The first alert came from customer support. Checkout is failing for some users. At first, it sounded like a minor issue. But within minutes, the sales team joined the incident channel. Revenue transactions were dropping. Customers were abandoning purchases halfway through checkout. Meanwhile, our dashboards looked perfectly healthy. Error rates were low. Latency was stable. CPU usage across the cluster was normal. From the monitoring perspective, nothing appeared broken. Yet real users clearly could not complete purchases. Our platform ran primarily on AWS. The back-end services lived inside a Kubernetes cluster on EKS. Around 150 pods handled API traffic, including authentication, product catalog, payment processing, and checkout. Traffic averaged roughly 5,000 requests per second during peak hours. The checkout service communicated with multiple internal services, including inventory, pricing, and payment authorization. The system relied heavily on microservices architecture. Each service exposed its own metrics through Prometheus. Prometheus scraped those metrics and stored them in a time series database. Grafana dashboards displayed aggregated metrics across all service instances. Alerting rules typically looked at cluster-wide averages. For example, checkout service error rate was calculated as the average error rate across all running pods. CI deployments were automated through GitHub Actions and Argo CD. Normally, the monitoring system provided reliable insight, but that day the metrics told a misleading story. Customer reports described an inconsistent pattern. Some checkout attempts worked perfectly. Others failed instantly. Customers refreshed the page and sometimes succeeded. Support agents noticed something strange. The failures appeared random. No specific region or product seemed responsible. The application logs showed occasional payment authorization errors. But nothing appeared severe enough to explain the complaints. Meanwhile, the Grafana dashboard showed the checkout service operating at 99.8% success rate. That number looked excellent. If anything, the system seemed healthier than usual. Yet the product team insisted that conversions had dropped sharply. The first hypothesis was a payment provider issue. Perhaps external API calls were timing out intermittently. Engineers examined logs from the payment integration service. The provider response times looked normal. Next, we checked database performance. High query latency sometimes caused checkout failures, but the database metrics were stable. CPU and connections remained within normal ranges. At this point, frustration started building. The system clearly had a problem, but every monitoring signal suggested the opposite. Someone decided to break down the metrics by pod instead of looking at the aggregated service graph. That was when the first clue appeared. Most pods showed near-perfect success rates, but one specific pod reported almost 50% failures. The root cause was a subtle bug introduced during the most recent deployment. One pod had started with an outdated environment variable. Instead of contacting the active payment API, that pod attempted to reach a deprecated endpoint that responded with intermittent errors. Because Kubernetes load balancing distributed traffic evenly, roughly 1/15 of checkout requests landed on that faulty pod. Those requests failed frequently. However, the monitoring dashboard aggregated error rates across all 15 pods. When the error rate was averaged, the service still appeared above 99%. From a metrics perspective, the service looked healthy. But for the unlucky users whose requests hit that specific pod, checkout was broken. The immediate fix was removing the faulty pod. We manually terminated the pod and allowed Kubernetes to start a replacement instance with the correct configuration. As soon as the new pod joined the cluster, the checkout failure rate dropped instantly. Customer reports stopped almost immediately. We reviewed the deployment configuration and discovered an incorrect environment variable introduced in a temporary testing override. The override remained active for a single pod. Once that configuration was removed, the cluster returned to a fully consistent state. Total incident duration lasted around 30 minutes from the first report until full recovery. What actually failed was our reliance on aggregated metrics. By averaging success rates, the monitoring system hid the fact that one pod was behaving catastrophically. The aggregated graph remained nearly perfect. This created a dangerous illusion. From an observability perspective, the system appeared stable while real users experienced failures. Organizationally, the dashboards had been designed to simplify operational visibility. But that simplification removed the ability to detect uneven behavior. Engineering lessons. Aggregated metrics should always be complemented by instance-level visibility. Dashboards should allow engineers to drill down. Alerting rules should detect outliers and anomalies instead of focusing exclusively on aggregated values. Configuration drift can create inconsistent behavior. Monitoring systems should reflect the experience of individual requests rather than hiding failures behind statistical averages. That afternoon reminded us that sometimes the numbers are not wrong. They are simply hiding the part of the system that is actually broken.